All right, so welcome to the Probability Lab. This lab, we're going to do two things kind of simultaneously. The first thing that we're going to do is model some distributions and use R to calculate the likelihood of picking a sample from within a certain range. And I think that that'll make more sense as we move on. We're going to start our examples with coin flips. So coin flips are wonderful because they can be represented by a binomial distribution. Binomial just means that there's two outcomes. So with a coin flip, you have heads or tails. As you might suspect, a whole lot of our world can be represented with binomial distributions. It's on or it's off, you're in or you're out, yes or no, all of these things. Anything that can't be represented with a binomial distribution is well represented with a forced binomial distribution. So, for example, if you have a three-way decision, let's say that you're classifying sentiment, and you have positive, negative, and neutral. Well, each one of those can be a binomial decision. You're either positive or not positive, neutral or not neutral, negative or not negative. And this allows us to more easily model a whole host of things, calculating the likelihood of each outcome. We are, however, getting far ahead of ourselves, and let's get started just with doing binomial distributions in R. Okay, R is super helpful, and it has a function that is just R binom. So we're going to go up here in the script, and we're going to type R binom. And we are going to flip one coin one time, and let's assume that it's a fair. Let's assume that there's a 50-50 chance that we're going to get heads or tails. Let's run that. First time we ran it, we got a, let's call one's heads 0 tails. We got tails. Let's run it again. We got tails again. Run it again. Tails. Wow, we are really hitting a lot of tails. There we go. We got a heads. All right. So run it until you get the same answer and you get a different answer. What this is illustrating is that this one thing that we've done here, this one coin flipped one time with 50-50 possibility, represents basically the most fundamental building block of all of our mathematical models. And I shouldn't say all, but a lot of things are represented binomially. Like this is the basic unit that predicts elections. This is the basic unit for financial forecasts, for weather, for diseases spreading. Most outcomes that we simulate, there's going to be an epidemic or there's not going to be an epidemic, are built on a series of these binomial distributions. So we are going to run a whole lot of experiments, and that's the second half of this lab, is that through this process, we're going to see how R allows us to create a whole lot of experiments that we just wouldn't be able to in the world. You just can't afford usually to run this many experiments, or it's just like not humane, or it's not like feasibly possible. But once you know once you know likelihoods of different events, you can start to model it. What's really cool about that is that you can calculate different potentials. So rather than 0.5, you can say, well, what if it's an unfair coin? What if it's 0.6 towards heads? Then you can model what would happen in that case also. All right, so that's all theoretical. Let's try another. So now let's flip 10 coins. So we'll call our binom, and we're going to pass it 10 coins. We're going to flip each one time, and they have a 50-50 likelihood. Okay, what we get out here is a vector. So the first coin was 0, the second coin was 0, third coin was 0. So we got 3 tails, and then we got like 4 heads, 2 tails, and a head. Okay, cool. This vector is really useful So there's two ways to do this. The other way to run our binom is one coin 10 times. We'll get to that in a second. But what's useful about having it be this vector, so this 10 coins one time each, is let's say you're doing a drawing and you want to randomly pick a winner. Like, let's say that you have a big Instagram poll and you want to randomly pick a winner, but you've ranked your winners somehow. You can use this vector and using position figure out who the winner is or who the winners are. So this vector gives us a bit of a different thing than one coin 10 times. All right, so let's look now at what one coin 10 times looks like. Slightly different. One coin 10 times, 50-50 chance. Run that, we get 6. What does that mean? Well, that means that our one coin came up heads 6 times. So rather than having 10 coins flipped one time, we have one coin flipped 10 times, and we only get one output. We can come up with a similar outcome if we say, let's have D1, and we are going to assign it to our binom. And we're going to have, again, our 10 coins, one time each, 50-50 chance. Run that, and then we'll sum our D1. And this gives us just a number, as opposed to the vector that we had before. So ultimately, you can get similar outcomes, but they are representing different things in the world. And you can leverage those different things in order to calculate different outcomes. For example, let's say that you are trying to find out what would happen if, a bunch of different events happen. Well, let's say that the first event has to happen in order to trigger the second event. Well, in this vector representation, the first event didn't happen, so the second event never happens. But had we gotten a 1 here for our first event, then it would lead us to another event. And you can have different outcomes for each one of these positions that each leads to another set of stacked events. So really triggering a cascade here. All right, so what if we instead want to flip 10 coins 10 times each? So before we do it, go ahead and make a prediction in your head. If we flip 10 coins 10 times each, what do you think we're going to get? All right, let's try it out. So we'll do our binom 10 coins, 10 times each, 50-50 chance. Run that. And we get a vector of sums. So we get, the first coin came up heads 4 times. The second coin came up heads 3 times. Again, this is really useful when you're trying to model different real-world events. Okay. Now let's try changing the probability. So let's make heads, or 1, more likely. In most situations where you're using probability, this will be your relevant, or your yes, or your on class. If you flip this around and you decide that you want your irrelevant, your off, your no class to be more prominent, word to the wise, unless you really have to do it the other way, make the number smaller. So, probability in a binomial situation is always 1 minus the probability is the probability of the opposite, right? So just do yourself a favor and don't try to flip the relevant and irrelevant or the yeses and the nos, because it gets very confusing very quickly. All right, so let's try changing our probability. Let's have our binom, and again, we'll use 10 coins 10 times, and now let's make heads more likely, and we'll say we have an 80% chance of getting heads. Maybe our heads is like weighted differently, or, I don't know, some way that your binomial is weighted towards the relevant class. Run that. And what you get here are much higher numbers, right? So here, whereas we were like somewhere around 5, you know, a little bit lower, a little bit higher. Here, we're somewhere around 8, a little bit lower, a little bit higher. This should come as no surprise given that our probability here was 0.5 and our probability here was 0.8. Now, that doesn't mean that it's impossible to get this vector of numbers with a 0.5 distribution. Completely reasonable to get the same vector for both distributions, but it is very, very unlikely. And as you move towards more instances, as we move away from 10 and we start talking about 1,000 or 1,000,000 or 100 million, then it really starts to distribute normally. It starts to distribute the way that we would expect given the probability that we've assigned. All right, so now just for fun, let's go ahead and change it so that the irrelevant class, or tails, or no, is more likely. So let's call our binom. We'll have 10 coins, 10 times, and this time our probability will be 0.2. Because like I said, it's very hard to switch it in your head. So just do 1 minus whatever. So now our irrelevant class, our 0, our no, is more likely. And here we have much lower numbers than we had here or here. You know, when our probability is 0.2, we're looking at numbers like 1, 3, 4, 2. When our probability is 0.8, we're looking at numbers like 8, 9, 7. And when it's 0.5, we're looking at 5, 7, 6, 4, right? So it's an easy way to quickly assign the variables. Okay, that's enough of that. Let's start to do something a little more complex. I'd like us to visualize the distribution to prove to ourselves that the likelihood of any given outcome is normally distributed. So we talked in class about the normal distribution and how everything that is naturally occurring is normally distributed. You know, it's centered around the mean, which in our case will be the probability. And then rare instances happen, but they are rare as we go out towards the tails. All right, so we are going to assign a variable, and we're going to call our variable flips. And flips is going to be our binom, so I have a binomial distribution of 100,000 coins flipped 10 times each with a equal likelihood, so a fair coin. All right, we'll run that, and then we'll just call hist on our flips, so force it into a histogram. Run that, and we see a perfectly normal distribution. You know, it's centered here around 5 is the most likely outcome. You can get 10, you can get 1, even 0, but the real likelihood is that you're going to get 5 on 10 flips. So what we're looking at here is the frequency of which a 5 occurred. So out of our 10 flips, it looks like a 5 occurred about 25,000 times, which is what we would expect because it's 1/4 of our 100,000. So yeah, we'll work that out in class a little bit better. Okay, converges on our normal distribution. That's interesting, and that's nice, but sometimes we want to see what the likelihood of getting exactly some number is. You know, what's the likelihood of getting exactly 5? So I flip my coin 10 times. How likely is it that I'm going to get 5 heads and 5 tails? So let's figure that out. Let's say flips, and we will set it to 5. Note that I am setting flips here with a double equals sign, not assigning a variable, but rather specifying a value, right? And I'm going to calculate the mean of where flips is equal to 5. Okay, I'll run this, and the likelihood of getting 5 heads and 5 tails, which is kind of what we would expect, is only just under 25%. So it's down here, 0.2463. crazy because, you know, if you're flipping a coin 10 times, you might assume that, oh, of course, if it's fair, you'd always get 5 heads and 5 tails. Or at least many people assume this. But really, the likelihood of getting exactly 5 is actually pretty low. It's more likely that you'll get something other than exactly 5. All right, that is kind of a complicated way to calculate that because we've set up this flips model. We had to assign our flips. We had to pass it to the mean. R is much smarter than that. R has given us D binom. So we are going to type D binom, and we're looking for exactly 5. So what is the likelihood of getting exactly 5 on 10 flips at a 50-50 distribution? Okay, you might be saying to yourself, wait, we didn't tell it how many coins. And that's true. We didn't tell it how many coins because we actually don't have to. So this formula is calculus based, and you do not need to have taken calculus in order to have taken this class. But all that you need to understand is that this is not a real experiment. Up here, when we were calculating the flips and finding the mean of where flips equals 5, that was a real experiment. We could get different results the next time. This is a mathematical likelihood assuming a normal distribution. So this, rather than telling it, oh, do this on 100,000 flips, what we're saying is do this as the flips approach infinity. So if you flipped coins from here to infinity and before and again, that is what we are modeling here. So let's go ahead and run our D flips. And we notice that we got a number very, very similar to our original number. We got 0.246093, and originally we got 0.2463. What that means is that it's actually slightly less than what our experiment concluded. So in reality, the mathematical likelihood of getting 5 flips is slightly less than what we got with our experiment. Okay, that is as complicated as it's going to get. And now we are going to move away from binomial distributions. And we are just going to start talking about normal distributions. So, as we've talked about in class, normal distributions are everywhere. Almost everything is modeled by normal distributions. The classic way to illustrate this, and honestly, I couldn't come up with a better idea on the fly. So the classic way to illustrate this is with height. So we are going to look at the height of American women. And it is well documented that the height of American women is about 65 inches or 5'5". What we know is that height is normally distributed. So some people are very, very tall, some people are very, very short, and the majority of people fall within at least 2 standard deviations of the mean. Our mean is 5'5", and our standard deviation is 3.5. So most American women are within 7 inches of 5'5". Okay, so let's model this. So rather than using a binomial distribution, we're going to use a normal distribution. So we'll say R norm, and then we're going to pass it 10,000 women. So we're taking a sample of 10,000 American women from the entire population of American women. So we have our 10,000. We know that the mean is 65 inches, and the standard deviation is 3.5 inches. All right, we'll run that, and we get a giant vector. So this is actually a vector of the heights of 10,000 women. This is almost impossible to look at and make any sense of. And therefore, it is a perfect use case for making a histogram. So let's assign the new variable heights, and we'll assign it to the normal model of 10,000 women who are on average, their mean is 65 inches, and the standard deviation is 3.5 inches. All right, so I have my heights variable, and now I'm going to make a histogram of my heights. I'll run that, and we get this beautiful histogram that shows a very nice normal distribution. You might notice that some, the slightly taller than 65 inches is slightly more common here than slightly shorter. Again, this is an experiment. It's not the actual mathematical model. Okay, so we might want to make the actual mathematical model. Now, I'm going to walk you through how to do this manually. This is completely optional. If you are not interested in the how this gets derived, if you're not interested in the calculus, just skip ahead a couple of minutes. Okay, so we are going to get started with our function. We're going to define our function as f is the function that takes x as a variable, and the function is d norm, where we pass it the variable x, and the mean of all of our women is 65, just like it was before, and the standard deviation is 3.5, just like it was before. All right. So it's the same exact function that we had here, except now we're using our d norm rather than our r norm. So our d, just like we used here, where we were finding the probability of a particular point. And what we're going to do now is we are going to find the area under the curve from that point to the tail, right? So this is where we're taking the integral. Okay, so we have our function, and we are going to say integrate. So we're going to take the integral of our function at the point 70 as it goes off to infinity. So this is everything from 70 inches to the left, or 5'10", no, to the right. So you can have positive infinity or negative infinity. We want to go to the right, which trails off towards positive infinity. All right, so we are going to run both of these sentences, and we find that the probability of finding a woman who is 5'10" or taller in the United States is about 7.7%, with this little bit of error that we're not going to worry about. This is sampling error that is not relevant to us right now. Okay, so you only have about a 7.7% chance of finding a woman who is over 5'10" based on the entire population of the United States. Okay, so if you haven't taken calculus and you don't want to do that, or if you're just lazy and you don't feel like taking the integral every time, and lazy is a positive attribute in programming, then you might just want to use p norm. So whereas we had d norm before, p norm tells us the probability of finding a woman who's 70 inches tall, assuming all women are, our mean is 65 and our standard deviation is 3.5. And we can go ahead and run that, and we get the exact opposite of what we had before. So if this is the probability of a woman being under 70 inches, or under 5'10". The way that p-norm works is it always calculates the probability from the left to the stopping point. So if you really just want to find the probability of finding a woman who's taller than that, it's really, really easy. You take 1 minus this function. So we'll go ahead and put that there, run this piece, and we get the exact same number that we had before, our 7.7%. All right, congratulations. You now have enough knowledge about probabilities to calculate the outcome of nearly anything. Binomial distributions and normal curves represent so much of our world that you really can calculate almost anything that you want to. Unfortunately, to calculate something using the normal curve, you need to know the mean and the standard deviation, and the binomial, you have to know the probability, which really narrows down how much you know or how much you can do, but it's still really empowering. Likewise, you should now know the difference between running an experiment in R and calculating a mathematical likelihood of an event occurring. All right, congratulations. Go ahead and submit your code, and I will see you in the next lecture. All right, bye-bye.